Welcome to our presentation on the topic of wireless EEG-ECG system for neonatal seizure monitoring and prediction. Neonatal seizures are the epileptic seizures that happen during the neonatal period. 1 to 3 per thousand neonates and 10 to 130 per thousand premature neonates suffer from neonatal seizures. These seizures can lead to death or disability.
For project deliverables, we present an EEG cap for neonates, wireless EEG-ECG module, AI model for neonatal seizure prediction, interpretability of the prediction model, and a publication to a journal. Our project consists of main 4 parts, namely front-end hardware, wireless module, processing unit, and a visualization unit.
We designed, assembled, and tested our system in 2 stages. This is the overall hardware design, which consists of the microcontroller PCB, ECG PCB, and the EEG PCB. Here we have our hardware design for the ECG analog frontend. It mainly consists of an ADS1292 IC, analog filters, and a voltage regulator. This is our microcontroller unit, which contains an ESP32S3, a lithium-ion battery, a battery charging unit, and a USB isolator. Currently, we have assembled the headset and successfully captured EEG signals from an adult test subject. What makes our design unique is its ability to switch between different electrodes, standard flat silver chloride electrodes or our own custom designed electrodes. Novelties of our hardware system comprise of EEG, ECG sensor fusion for neonatal applications and custom 3D printed electrodes we modeled, printed, and assembled ourselves. These electrodes are printed using a conductive 3D printing material with spikes as small as 350 by 400 micrometers in cross-sectional area.
We were able to validate our EEG headset with an EEG machine at LRH.
When Hansa blinks his eyes, you can see an artifact on the top graphs, and those are from the electrodes which are connected above the eyes. Now, as Hansa is clenching his teeth, you can clearly see the muscle artifacts in the EEG graphs. Now, Hansa is closing his eyes to remove the effect of visual observations. When you observe the bottom 2 graphs, you can identify the alpha waves, which are gathered from electrodes connected to the back of his head. The top graph refers to the respiratory signal, and the bottom graph represents the real-time 3-electrode ECG signal acquired from Hansa.
A seizure has 4 main stages: interictal, preictal, ictal, and postictal. The interictal period is when the patient is in a normal state. The preictal period occurs just before seizure onset. Seizure prediction involves distinguishing between the interictal and preictal stages. Most existing seizure prediction models are patient-specific and primarily focused on pediatric adult populations. At Brain Neocare, our team developed a neonate independent seizure prediction model leveraging explainable AI to enhance model interpretability. We used the publicly available Zenodo neonatal scalp EEG-ECG dataset with seizure annotations to train and test the model. The dataset consists of 79 term neonates admitted to the NICU of Helsinki University Hospital. Additionally, to further validate our model, we used the CNR dataset, which consists of data from 14 adult epileptic patients. After testing various feature types, we selected Mel-frequency cepstral coefficients as the input features due to their superior performance. So the model input is stacked MFCC matrices from EEG and ECG channels with a channel dimension of 19. This is the architecture of the proposed seizure prediction model. It consists of 3 convolutional layers, followed by a squeeze and excitation layer. Finally, the dense layer outputs the probability that an input sample belongs to the preictal period. We performed tenfold cross-validation to evaluate the model's performance. Our model achieved over 95% across all 4 evaluation metrics. Here, we present a comparison of our results with existing patient-independent seizure prediction models. This is the channel-wise shape representation, highlighting the tendency of each electrode location to contribute to a seizure. Red-colored electrodes indicate locations where preictal features are prominent, while blue-colored electrodes correspond to regions where interictal features are dominant. Using the shape values, we are able to visualize the scalp area of seizure activities. To further validate our results, we tested our model on an unseen seizure of an unseen neonate. For that, we fine-tuned the model using the earliest interictal and preictal data of the unseen neonate. These are the results we obtained for an unseen seizure of an unseen neonate for the fine-tuned model. The results are compared with a model that was trained from scratch using the fine-tuned data. These are the results for the ablation study we conducted to evaluate the effect of the attention layer and the addition of ECG data for model training.
We are Agastya Putantri, Hansa Marasinghe, and Setmini Ranasinghe, who are final year undergraduates at the University of Moratuwa.